Hello, today we will finish off the Laplace transform by showing that it can do more than what we saw in the previous lecture, essentially. Let's start with some motivation. A linear differential equation may, among other things, also describe an electric circuit, and in such an electric circuit, those components are not always active. For instance, imagine that you have a source which is sending in a sine wave, but this sine wave switches on later than at time 0, so it goes like that. Time 0 here, and nothing's happening. There is no input from the source until time, let's say, pi. And now the sine wave jumps in. So here is the first hill, and then it continues like that. So this is a function ft, which would appear in our differential equation. How would I write it mathematically? That's a good question, and we know the answer. This is in fact a function defined by cases, so I can use the notation for a split function if you want. Okay, ft is 0 if t is less than pi, and if t is sine t if pi is less than or equal t. I'm going to follow the order from smaller to the larger so that it sort of sends the right message. Okay, let me fill in some details, and that's one way of writing such a function, which is a good way, but sometimes it's not exactly convenient. We would prefer something which is like an algebraic formula. And there is a way, and in fact we more or less know it already. ft is sine t times the Heaviside function. Now we know, we saw it before in the previous lecture, that when we multiply a function by the Heaviside function, then we are in fact killing it off on the negative half axis. So what I'm going to do, I'm going to shift the argument in the Heaviside function. And now let's see what it does. If t is to the left from pi, less than pi, then this argument is negative. Heaviside function of a negative number is 0, and this whole thing is 0. Yeah, that fits. If t is more than pi, then the argument is positive, the Heaviside function is 1, and we get our sine signal. Wonderful. So that's exactly the same thing, just written in a different way, and this one looks more compact, more convenient for certain purposes. There's actually more to it. Let's have a look at this function. h t minus a minus h t minus b. Now it should be said that a is greater than or equal to 0 and b is even farther to the right. So that's the setting. What can I say about this function? Well, let's have a look at it. I'm going to make a little chart here. First we will just investigate h t minus a, then h t minus b, and we will do it on some intervals. And there will be 3 of them. Okay, here's the plan. And I can make a picture too. T and a is to the right from 0, so let's say here, and b is somewhere more to the right. Why not? Okay, let's see. First, what happens when t is to the left of a? Well, let's start here. If t is to the left of a, then this number is negative and also this number is negative. So both Heaviside functions are 0, and when I subtract them, I get 0. That's what I'm interested in. Okay, 0 all the way here. Now, once we hit a, something changes, and this will be happening until b. So for t between a and b, a included, the situation is as follows. T is to the right from a, it's over here, so this number, this argument is positive, or 0, and the Heaviside function is 1. On the other hand, if t is between a and b, then t minus b is definitely negative, and this Heaviside function is 0. When I subtract them, 1 minus 0 is 1, and we have a nice steady signal on the level 1. All the way up to b. What happens once we pass b? This argument is positive, definitely. And this argument is now also positive, or 0. When I subtract 2 ones, I get a 0, and we keep going like that. So as you can see, this difference, where a is smaller, b is larger, creates a step of size 1. Some people call this a finite signal. And if you are unhappy about the shape of it, you can shape it further just by taking this expression and multiply it by some function. So you can moderate it in this way. Let's put it in a slide. So this actually captures one possible point of view. You know that something is happening in a specific time interval. So you start by creating such a basic step or basic finite signal or whatever you want to call it, using the difference of Heaviside functions. And then you give it a shape by multiplying this difference by a specific formula. And on the right, we can see using the split notation the meaning of that. But actually, the basic idea is more general. You are simply looking at it and thinking, okay, I'm switching on and switching off something, and I can keep going. I don't have to stop after 2 actions. So let's have a look at this other point of view. You have a shape in mind, let's say e to negative t, but I'm not going to call this picture e to negative t. This is just the basic shape, which I have here at my disposal. And now I decide that I want to switch on and switch off a signal which is based on this basic shape. So let's say that I decide to switch it on at time 0. Sounds like a good time. So I'm switching it on, and it goes on until time, let's say 2. Why not? Okay, so definitely the scale on the horizontal and vertical axis is not the same. Doesn't really make a big difference. Anyway, at times 2, the signal stops, so it's actually a 0 signal. Until time, let's say 5 over here. And at time 5, my original shape gets on again, and I keep going. So it's not a finite signal anymore because it doesn't stop, but it follows the general idea. How would I write such a signal? Well, I start by writing down the shape formula, which is e to negative t, and now I go from the left to the right. So first, I have to switch it on. Heaviside function, shift it so that it works at time 0. Okay, this is the first, and I'm sure last time that I'm writing it this way for pedagogical reasons to explain the idea, but I'm too lazy to do that more than once. Now I'm switching off. Switching off means subtraction. So I'm switching off the signal at time 2, and then I switch it on, which means plus. Signal at time 5. And if I wanted to switch it off, there would be another subtraction, and so on. I can keep going like that, creating all kinds of crazy signals. Okay? So that's a very simple and quite powerful idea, in fact. So now we know how to write down those finite signals. And the good question is, okay, I have a differential equation, and there is a finite signal in it, something like that, and I want to use Laplace transform to solve this differential equation. How do I transform function of this type? And actually, I could go by definition, but perhaps that's too much work. So instead, I'm going to introduce a new grammar. Here we are. And the first formula, that's what interests us. We have a function, we multiply it by a shifted Heaviside function, and we want to perform Laplace transform. Let's prove it. Why not? I'm trying to apply the Laplace transform to a function f t minus a, h t minus a, and I get a new function in this other world of functions that accept s as the variable. So what is the value of this function at point s? And definition says you just integrate from 0 to infinity your function f t minus a, h t minus a, multiplied by exponential where s features as parameter. Okay, that was it. So this is what the definition says. And now I'm going to get rid of those shifts using linear substitution. So this should be easy. I take t minus a, and I call it, let's say, u. I didn't have any u here today yet. Okay, let's work it out. So, well, Well, integral f u h u e to negative s times, and here we have to think a little bit. T is u plus a. So far, so good. Now, that's just a shift substitution, so the differentials, they just carry over like that. This is also easy. And finally, we should change the limits. So for t, we have limits 0 and infinity. And then from that, using our formula, if t is 0, then u is negative a. And if t is infinity, then infinity minus a is infinity again. So my new integral goes from negative a to infinity. Now, let's play with it a little bit. First of all, this Heaviside function, and therefore this whole thing, is 0 if u is negative. And therefore we can start integrating from 0. That's the first important observation. And go to infinity, fu hu. Next, here we have this exponential. And this exponential is in fact e to negative su, negative sa. And we can split it as a product. It's e to negative su times e to negative sa. Now a is a constant. It's a shift in our formula. And s is also a constant right at this moment. That's the fixed value for the variable. So this is a constant which can be pulled out. E to negative sa, and the remaining part has to come here because the working variable is in it. Okay, now we just look at it and we say, oh, okay, here is the constant, e to negative sa. And this is the Laplace transform of the original function unshifted. So, okay, it's traditional to use t for that. I don't have a problem with using t here. And the value is s. Great. Does it work? Yes, it does. So, let's have a look at the idea behind this rule. Let's not follow it formally. We have a function, we want to perform the Laplace transform on it. So, we need to shift the arguments by a. We want to add a to both arguments. And we can do it in exchange for extra exponential. This form is easy to prove, as you can see. It's sort of natural fit for the proof. But perhaps you wonder about the shift over here. Okay, we have a shift over here, but we don't have it here in our examples. For instance, here I'm shifting in the Heaviside function, but I'm not shifting my shape function. So perhaps the last formula would be more convenient. Notice, and that's the important part, it actually follows the same basic idea. You have some formula in your Laplace transform on the left, and you want to add a to the variable. And you have to do it at both locations. You have to shift the argument both with f and the Heaviside function. So in the first and in the last formula, you are doing the same action. You are simply adding a to the variable t or t minus a, whatever. And after you shift, as a punishment, you have to add the extra exponential. So in fact, these two rules are just two possibilities how to express the same thing. The intermediate rule, that's a rule that we use when we are doing the inverse Laplace. And it's essentially obtained just by reading this formula from the right to the left. No big problem there. Okay? So that's the new grammar. And let's try it on a few examples. We will see how it works. For our first example, we will transform the exponential into 2t, which starts with a delay. And we will make 3 attempts, and the first attempt goes by definition. Because for this example, it's actually, let's say, a reasonable approach. So how does it go? Well, we have to integrate from 0 to infinity the function inside those curly brackets multiplied by e2 negative st dt. Let's see. Well. This Heaviside function, and therefore the whole thing over here, is 0 for t less than 1. So what we can do, we can simply ignore everything which happens before 1, and we just integrate from 1 to infinity. Once we pass 1, this Heaviside function becomes 1, and we can ignore it as well. And there's just two exponentials. Let's put them together. It's e2 t times 2 minus s dt. And this is easy to figure out. So let's see. We have to integrate using substitution, which is a fairly routine business by now. So we are dividing by 2 minus s because that's a constant in this context. And we go from 1 to infinity. First, we substitute infinity into the picture. And the way I see it, s should be more than 2, so that we get a nice convergent answer. This is the usual trick. And if s is more than 2, then we get e to negative infinity, which is 0, no problem there. Then we are subtracting, and we are substituting 1 into the picture. So we are getting e to 2 minus s divided by 2 minus s. And now I'm going to work it into something nicer. And I think it will be good if I write it as e squared times e to negative s times 1 over s minus 2, s greater than 2. So that's my first attempt. I go by definition. I have to do a little bit of reasoning, but it's okay. Let's try it again. I will use the first formula, the one that I just proved. Here we are. I'm trying to transform a function multiplied by shifted Heaviside function, but the formula expects also the function to be shifted. So I have to do some preparation here. Laplace transform. And what I would really like to see is exponential with 2 times t minus 1 in the argument. Do I have it there? No. So this is cheating. To fix it, I have to add 1. So far, so good. And now, I'm going to apply a little algebra here. So I take this exponential and I split it as e2 2 times t minus 1. This is what I want. Then there is extra plus 2. So I will split it further as e squared, that's this part, e to the power 2, multiplied by e2 2 times t minus 1. And that's the part that I like. So this is the part which is here sitting in my Laplace transform. Laplace transform is linear. So if I see a multiplicative constant, and I do, e squared, I can pull it out. And I'm applying Laplace transform to this remaining part, e2 2 times t minus 1, Heaviside function t minus 1 at some s. And now I'm in position to use my grammar. So instead of the shift t minus 1, I will just put t. Laplace transform e to 2t, Heaviside function t at s. However, I pay for it by putting e to negative s times the shift, which is 1. S times 1. And I shouldn't forget e squared. It was sitting up here in front of the expression. So far, so good. So far, so good. Now let's work it out. E squared times e to negative s. What is the Laplace transform of e to 2t? I remember this one. It's in my vocabulary or dictionary. 1 over s minus 2, s greater than 2. Is it the same answer? Fortunately, yes. So, is it faster? Perhaps yes, a little bit. Especially if you have some experience and you can do these things, easily. Okay, attempt number 3. This time I'm going to use the alternative formula, which is in the last line. So, I don't have to really do any preparation. I'm simply applying it over here. I have a formula, that's ft, and I have a shifted Heaviside function in it. So, what does the formula say? It says, put an exponential up front, minus s times, multiplied by the shift, which is 1. And then apply Laplace transform to your function, but shift it in the opposite direction. So essentially, as I explained, I'm adding 1 over here, and I also should add 1 over here. So it's e2 twice t plus 1 Heaviside just t at s. And that's it. We just applied our grammar, and it seems that we are done. But we are almost done because e to 2t plus 1 is not in our dictionary. So again, we have to do some algebra. E to negative s, Laplace transform, and this is e to 2t. Okay, let me do it here again. This is e to 2t plus 2, which is e squared times e to 2t. And again, e squared is a constant. I can pull it out. But I already started to write, so okay, let me do it properly. E to 2t, heaviside t, s. And now I will pull out e squared. And I'm just applying Laplace transform to e to 2t, heaviside function. And let's see, it's e squared e to negative s. And the Laplace transform of e to 2t, I've been doing it a few seconds ago, so I remember how it goes. And we have the same answer for the third time, so we are slowly beginning to believe that this is correct. Wonderful. Which of these ways is most convenient? I would actually go with the latest one, with the third one. But as you can see, it's not that much different from the second one, because we had to do some algebraic trickery with the exponential here and also here. And it was essentially the same trickery. So when you are comparing the original version of the rule and the, let's say, updated version of the rule, they are essentially both requiring that you do some algebraic work, which is essentially the same. The difference is at which stage you are doing this work. This rule, the original version, requires you to be proactive, while the second rule is reactive. So here you have to think ahead and adjust your problem so that it fits. And there are situations where this is actually, let's say, convenient. And especially there are people who like being proactive, so perhaps this is the rule for them. Here, you don't really have to worry about what type of operations you want to do. You simply apply the rule, and then you say, oh, wait a second, there is this thing over here, I have to react. And you react in essentially the intuitive and natural way. So that's why I think this alternative version, which we can see on the last line, is perhaps somewhat more convenient, somewhat preferable. I think I usually prefer this way number 3. Anyway, let's try another example. Laplace transform of the following shape. It's actually the sine function just taken between 0 and pi, and it's 0 elsewhere. How do we transform it? Well, we could try to go by definition. So we have to integrate our function multiplied by e to negative st dt. How do we integrate this function? Well, it's 0 before 0 and after pi. So we can ignore those parts in our integral. We just integrate from 0 to pi, and the function is sine. Now, integrating sine t times exponential is not exactly pleasant. One has to use integration by parts twice. One gets an equation. This has to be solved. Perhaps, okay, if you really want, go ahead, enjoy yourself. I'm going to follow an alternative route. I'm going to use grammar. Namely, I will go for the last row, this, let's say, slightly more convenient version. So how does it go? First of all, we have to write this hill using the Heaviside functions. So the basic shape is given by the sine function, and I switch it on at time 0, and I switch it off at pi. So far, so good. Now, let's see. The rule says, well, I cannot apply it, can I? There are two Heaviside functions, and they are different. So, what I have to do, I have to multiply the sine function out in this bracket and split it into two Laplace transforms. Fortunately for us, Laplace transform is linear. So it will be Laplace transform of sine t, Heaviside function, at s, minus Laplace transform of sine t multiplied by the shifted Heaviside function at S. Okay. The first Laplace transform, I like that one because it's in my dictionary. We saw it previously in the previous lecture, and it's 1 over s squared plus 1. Good. Now, how about the second one? Well, we are ready for the rule. It says you can shift the argument. Let me do it. I'm shifting the argument, so I will get sine t plus pi, Heaviside function just t. I like that. And as a punishment, I have to put e to negative pi times s. Pi is the amount of shift which I'm performing here. Okay. Now I don't have a shift with the Heaviside function, but I have a shift in the sine function. But fortunately for me, this I can handle using algebra. So either you are really familiar with the sine function and you know that this is minus sine t, or perhaps you are not all that familiar with the sine function, but they forced you to memorize some identities when you were a kid at high school, and you remember what is sine alpha plus beta. This is sine t cosine pi plus cosine t sine pi. And now sine of pi is 0, so this is gone, and cosine of pi is negative 1, which gives you negative sine t. Here we are. Either way, let's work it out. 1 over s squared plus 1 minus e to negative pi s. So far so good. And now, instead of sine t plus pi, there will be minus sine of t, and this minus can be pulled out. So I'm still multiplying by negative 1, applying the Laplace transform just to the sine function. And that's something that I've done before. So this is 1 over s squared plus 1. Minus and minus give me plus e to negative pi s 1 over s squared plus 1. And that's it. If you want, it's not necessary, but perhaps it's elegant. We can write it as 1 plus the exponential times 1 over s squared plus 1. Is it better? I don't know. So there are two versions. Pick whichever you like. Okay, so we saw two examples of using our new grammar to send over in the Laplace transform a finite signal. This is actually fairly typical. And this is a trick which is used quite a lot. To finish this part off, we are going to try the inverse Laplace transform, which is the middle rule. Okay, imagine that you are trying to solve a linear differential equation using Laplace transform. So you transform it into the world of S. It becomes an algebraic equation. You solve it. You get this function. And now we are trying to go back to the original world of t. So here, the outcome of this inverse Laplace transform is some function with the variable t. And you are thinking, okay, is this guy somewhere in my dictionary? And the answer is no. So we want to use some grammar. So perhaps we should separate. Let's take this exponential away to isolate it, and then there is something left. Now, in the inverse Laplace transform, we don't know what to do with the exponential, but we do know what to do with this guy. It actually transforms to cosine function. So, we are interested in a rule which would allow us to drop the exponential and just focus on this fraction. And fortunately for us, that's exactly the rule for the inverse Laplace transform that we can see over there. So what does it say? Well, it says, drop the exponential. Okay, I'm happy to do that. And just find the inverse transform of whatever is left. So far, so good. But when you are done, you substitute into the outcome a shifted variable t, and you multiply it by the shifted Heaviside function. Okay, I don't have any problem with that. Now, as I said, this is something that I remember from the previous lecture. This was in a dictionary. That's cosine. But now I have to do the delay substitution. Well, perhaps I can write it like that. so that we can see what's happening. And finally, I substitute in, I get cosine t minus pi, Heaviside function t minus pi. And I guess you could leave it like that, but it looks awkward. So let's think a little bit. Cosine t minus pi is nothing else but minus cosine t, and then it's multiplied by the shifted Heaviside function. And in case somebody's curious, or sometimes it's actually quite useful, we can figure out what it means. This shifted Heaviside function is the key. Everything begins at time pi. Before time pi, there is nothing happening. We get 0, t less than pi. But once time reaches pi and moves on, this Heaviside function becomes 1, and we get minus cosine. So this is for t greater than or equal pi. And again, some commas and things like that, and we are done. And actually, looking at this, it's easy to visualize what's happening. So just out of curiosity, we all know and love the sine function and the cosine function. We know how they look like. Now, when we put minus in front of them, they get flipped around. So minus cosine essentially has this as the basic shape, and then it's just repeated over and over. But now, I'm ignoring it until I hit time pi, which is over here. This is pi. So my signal is 0 all the way here. And at pi, it hits the minus cosine curve, and it takes it. And gets on with it until the end of time. Go ahead. So that's my f. That would be the solution of my differential equation in the story. The bottom line is that applying the inverse rule, this particular inverse Laplace rule, is quite okay. We just have to remember about the shift and be able to work it out later on. Sometimes, when you can see the inverse Laplace transform immediately, when you don't have to worry about it, and you don't have to work on it, it may be more convenient to use the little f, capital F way of writing grammar. So if I know that a function f is related via Laplace transform to function lowercase f, ft, fs, to emphasize it, then we can perhaps write that the inverse Laplace transform of e to negative a s, fs, is simply lowercase f t minus a, Heaviside t minus a. That would be the alternative way of writing this rule, which is good if you can go immediately from this part to this part using inverse Laplace transform. But if this step requires more work, or if you don't want to do too many things at the same time, this rule allows you to sort of decompose your process into more steps. Perhaps it's more comfortable. Okay, so much for the Laplace transform of finite signals, an inverse Laplace transform. Now we are ready to try it out with some differential equation. Here we are, a nice linear differential equation with a funny right-hand side. Now, if this differential equation were describing an electrical circuit, then what we see on the right would be an electric source. And obviously, this one is switched on only for a short while, for 1 second. And then it switches off again. So actually, this is a finite signal which has a really nice shape. 2 initial conditions. So this is an initial value problem. We will try to solve it using the Laplace transform. But for that, we would need the function on the right to look differently. So that would be our first step, preparatory step. The second derivative of x minus x is, the basic shape is 2, and it switches on at time 0 and switches off at time 1. One more preparatory step. This is 2 times the Heaviside function minus 2 times the shifted Heaviside function. Okay, now we are ready to apply the Laplace transform to both sides of this equation. So we move it to this other world where the variable is s, and we will see what happens. Applying Laplace transform on the left, we notice here is a difference of 2 functions. Laplace transform is linear. We did things like that in the previous lecture, so we are not surprised. And we also have to use the rule for the second derivative. Here is an updated list of our dictionary and grammar, and on the right, 1, 2, 3, the fourth line, that's exactly the rule I'm looking for. So it says, instead of applying Laplace transform to the second derivative, you apply just to x. Nice. But of course, it doesn't come free. So as a punishment, we have to multiply this Laplace transform, when it is done, by s squared. And then we have to subtract a little tail. S times the value of x at the origin taken as a limit from the right, and the derivative of x at the origin from the right. So that's the rule for the second derivative. Now we subtract Laplace transform applied to x, and we go to the right. Again, difference of two expressions, so we apply Laplace transform. On the left, I use linearity. I pull out 2, and I'm just trying to find Laplace transform of the Heaviside function, which is 1. Laplace transform of 1. That will be easy. On the right of this difference, I'm going to keep it as it is. And you will see shortly why. Okay, so far so good. Now, Laplace transform of the function x is some function in the target space. Let's call it capital X, which is traditional. Capital XS. Let's emphasize the variable so that it makes sense also to write s square in front of it and it sort of fits. We see what's happening. The initial values, we have them here, allow us to drop these two terms in the tail of the second derivative rule, which is nice. Then we are subtracting capital XS. And let's see what's happening on the right. Twice, we transform the constant function 1. And we see it in the dictionary, 1, 2, 3. Again, it's the rule number 4 in the left column, 1 over s. And now we're subtracting, and there is a function f, which is 2, multiplied by shifted Heaviside function. So we have to use the shifted rule, which we can see the second line from the bottom, and it's the convenient form. So let's apply it. First of all, we are shifting by 1, so as a punishment, we have to put e2 negative 1 times s. And then we are applying the Laplace transform, and now we have to shift argument in both functions. When we shift it in the Heaviside function, it will become just ht, easy. And shifting argument in a constant function just leaves it alone. Because shifting argument means we are shifting the graph left and right. And if it's a constant function, shifting the graph left and right doesn't really influence it. Or you can simply argue that there is no t, and if there is no t, then there is nothing to change. Easy enough. Okay, I think we are ready. So we have s squared xs minus xs is equal to 2 over s minus e2 negative s times, and the Laplace transform of two Heaviside functions, we have done it before. This is again 2 over s. Wow, nice. One would be tempted to put these two guys together, but it's not exactly a good idea. Okay, so let's make one more step. I'm going to factor out xs, because that's what I'm aiming for. And then there is s squared minus 1, which is nice. And on the right, we have 2 over s minus e2 negative s 2 over s. And we are ready to solve our equation. Finally, how much is xs? xs is 2 divided by s times, and let me put it this way, s minus 1, s plus 1. Okay? S squared minus 1, I just factored it out into two factors. We will need it. e to negative s, and the same thing over here. So this is really a luxurious example, because it's easy. I have two partial fractions here to be done, but they are the same. Saves me some work. That's my solution, but it's the solution in the world of the functions of s. We have to go back. We have to apply the inverse Laplace transform. Before we do that, it's time for these partial fractions decomposition. We remember from previous lecture, that's the way to go. We just need simple fractions. So, what do I see? there will be some constant divided by s, plus some constant divided by s minus 1, plus some constant divided by s plus 1. Definitely. What constants will these be? Well, I can actually use the hiding trick from calculus 1. That's my favorite. For linear factors which are distinct, this is perfect. So to get a, I cover s, and I substitute the root, which is 0. I substitute 0 here, and I get negative 2. Okay, I can live with that. To get b, I look at the root, which is 1, and I substitute it here after I cover up the factor. I'm substituting 1, 1, 1, b is 1. Okay. C, the root is negative 1, and I'm substituting it here. Negative 1, negative 2, it's negative 1, negative 1. It's 1 again. Wow, that's neat. Okay. I'm subtracting e to negative s and the same decomposition. Do I want to change the order? Perhaps yes. I don't like starting things with minus. So it will be 1 over s minus 1 plus 1 over s plus 1 minus 2 over s. Here we are. That's the partial fractions decomposition. And now I'm applying the inverse Laplace transform to get back to the original world of functions xt. And let's see. 1 over s minus 1. That's in my dictionary. That's the very first rule. 1 over s minus 1. This is just e to t. And it's also here. This guy is the same rule, but alpha, in this case, it's negative 1. So it's plus e to negative t. Then there is twice subtracted, or here, twice subtracted, the Laplace transform, inverse Laplace transform of 1 over s. 1 over s goes to 1, so it's just 2 by 1, which is 2. Okay, so this is the inverse Laplace transform of these three factors, but here we have to do some work, because I can see those factors, but there is also extra exponential in it. So when I'm applying the inverse Laplace transform, going this way, I have to use the special rule, which we can see in the last line. So I would have to actually do the Laplace inverse transform of 1 over s minus 1 plus 1 over s plus 1 minus 2 over s. Substitute t minus how much? The constant here is 1. T minus 1, and multiplied by a Heaviside function, which is shifted, t minus 1. That's what the very last rule says, and we saw it just a few minutes ago. I know how to do the inverse Laplace transform of this family. I just did it over here. So my function xt is e to t plus e to negative t minus 2 minus. Now I do the inverse transform, which is this, and then I'm substituting t minus 1. So it will be e2 t minus 1 plus e2 minus t minus 1 minus 2. Again, there is no t in it, so shifting the argument doesn't make any difference, times h t minus 1. And I could leave it like that, definitely. But again, for the user or for the reader of our solution or interpreter of our solution, it may be nicer to write down what's really happening. So, definitely, we are getting, well, there is actually a Heaviside function hiding. As I said, people are too lazy to write it, but in fact, there is ht. So everything is 0 when t is less than 0. When time 0 kicks in and moves on, the second term is still 0 because ht minus 1 is waiting for time 1. But this term kicks in. E to t plus e to negative t minus 2. This is for t's between 0 included and 1 sharply. Semicolon here, or something else. Just out of curiosity, this solution must be continuous. Is that true? What happens to this formula when time is 0? I put 0 here, 1 plus 1 minus 2 is 0. Yes, I have a nice continuity. There should also be differentiability there. So if you find the derivative of this and you put 0, you will get 0, which is the derivative of this. Also, the derivative follows nicely. There are things like that that one can check. Anyway, now it gets really interesting. One value, and now we have to figure out what is the value when t is 1 or more. And this is where it gets interesting. So I think it will take a little bit of work. So what are we getting? When time is 1 or more, then this heaviside kicks in, and we are getting e to t plus e to negative t minus 2. But also the second heaviside function kicks in, and we are getting e to t minus 1 plus e to t minus 1 minus 2. This is what we are getting for large times. Can we simplify somehow? That's a good question. Well, definitely the 2's they cancel. So one possible way to write it is e to t minus e to t minus 1, for instance like that, plus e to negative t minus e to negative t minus 1. There could be one way. Or perhaps we can factor out e to t, and we get 1 minus e to negative 1 times e to t. That looks good. And then in the second term, we get 1 minus e times e to negative t. That also looks nice. Do I have any preference? Not really. Anyway, all these three formulas, they are valid for t which is greater than or equal to 1. And that's the way the solution looks like. Can I visualize it somehow? Probably not. I would ask Maple or some other graphing program which can do it for me. Probably. Again, let's talk about continuity. What's happening when time is 1? That's a good question. It's not really necessary, but I like to do that because if I make a mistake in my calculations, then this check sometimes discovers it and makes me worry and recalculate the things. So what's happening with the middle formula when we reach the time 1? 1 here, 1 here. We are getting e plus e to negative 1 minus 2. That's the value. What's happening with the second formula when time hits 1? So when it starts. I think the middle formula will be the best. So when time is 1, it will be e to 1 minus e to 0, which is 1, plus e to negative t, which is e to negative 1, time is 1 now, minus e to negative 1 minus 1 is 0. This is minus 1 again. Are they equal? And the answer is yes. This is e plus e to negative 1 minus 2. So there is a match. Again, these two formulas, they flow nicely into each other. If we find the derivative here and substitute 1, and if we find the derivative here and substitute 1, again, they should match. Okay? So this creates a function which actually consists of 3 segments. 0, nice segment, more complicated segment, and they all together give you a function that has the second derivative, and the first derivative is continuous. Notice that the right-hand side is not continuous, so the second derivative here need not be continuous, it will not be continuous. Okay? So much for the Laplace transform. Did it handle our problem? The answer is yes. And in fact, when we look back, that wasn't too bad. I mean, handling the shift, we know how to do that. Solving algebraic equations easy. Here, perhaps the partial fractions could be sometimes more difficult, but that's just a technical part, no problem here. Inverse Laplace transform was also okay. And if you are happy with this answer, then we could have stopped much earlier. Okay? So that's fine, I would say. Here is one possible answer for those who are happy with just some formula. And here is the other answer for those who like to have a little bit of hands-on feeling for what's happening. So the Laplace transform can handle equations with discontinuous right-hand side. Nice. Good question. What if We were asked to solve this equation before we learned Laplace transform. Could we solve it using standard tools? And the answer is actually yes. How would it work? First, we would solve this equation for times between 0 and 1. That would be stage 1. So the equation reads x second derivative minus x is 2 with initial conditions x naught is 0, x derivative is 0, and we are handling it on interval 0, 1. That's important. So let's solve it. First of all, we need to find the homogeneous solution. Over here, characteristic polynomial lambda square minus 1 is 0, lambda is plus or minus 1, so the homogeneous version of the solution is a times e to t plus b times e to negative t. That was easy. Now for the right-hand side, we would use the guessing method. So the particle solution would be some constant. Is there an overlap with lambdas? Here lambda is 0. Here lambdas are plus or minus 1. There is no overlap. So we just put a as our guess. And let's have a look at it. We take a, we substitute into the second derivative, it disappears. Minus a is 2, a is negative 2. So the solution, the general solution for the first part, let's call it x1. x1t is, well, perhaps it's not x1 yet. I will erase it. I will get to it soon. So xt is a e to t plus b e to negative t minus 2. That's the general solution. But now the initial conditions kicked in. So initial conditions say that when we substitute time 0 into this formula, we should get 0. So I'm substituting 0 for time, and I'm getting a plus b minus 2 is 0. So far, so good. The second initial condition says differentiate and then substitute 0. I'm differentiating and then substituting 0. I'm differentiating and then substituting 0. I'm differentiating, and this should be also 0. So a is b and must be 1. And now I'm going to write x1. That's the first stage, so to speak, of our solution. A and b are 1, so we are getting e to t plus e to negative t minus 2. That's the formula for t from the interval 0, 1. Is that the same? And the answer is, if I remember correctly, yes. Yeah, that's exactly the right formula. Okay. Now at time 1 we stop and we start solving a totally different differential equation. X second derivative minus x is 0 because that's the new right-hand side over here after time 1. We solve it easily because now this is a homogeneous equation. So what is the solution? Well, the general solution is xt is equal to, well, it's exactly this formula. A e to t plus b e to negative t. But here we are solving for t greater than or equal to 1. That's important. What are the initial conditions? That's the tricky part. We cannot use these because they are at time 0, but here we are solving from time 1. So what are the initial conditions? They have to be taken at time 1. And our requirement is that the new part of the solution joins neatly with this part of the solution. So we should look at our function x1 at time 1, and we should look at its derivative at time 1. So what is the value of our function at time 1? Well, we did it actually before when we are checking whether things connect or not. So we are getting e plus e to negative 1 minus 2. That's the value of our solution. And then we have to differentiate and substitute 1 into it. So we get e to 1 minus e to negative 1. So that's the new set of initial conditions for us. General solution, initial conditions, well, there must be a way. I substitute 1 now. ae plus b e to negative 1 is this expression and I differentiate and substitute 1. And that should be the second condition. Okay, looking at the second equation, it would be tempted to guess that A is 1, B is 1, but then the first equation doesn't work. So it's not going to be that easy. Let's say if I add these equations, I get 2AE is 2E minus 2. Okay, so A is, and now let's see, I divide by 2, I divide by E, and I get 1 minus e to negative 1. So 1 minus e to negative 1 is the coefficient before e to t. And that's exactly this part. Wow, we are getting a match. Good. If I take the first equation and subtract the second equation, I get 2b e to negative 1 is equal to, I'm subtracting. So b is, I divide by 2, that's easy enough, and I multiply by e. And by remarkable coincidence, that's exactly this coefficient. So the second component of our solution is 1 minus e to negative 1 e to t plus 1 minus e to negative t greater than or equal to 1. And when these two components are put one after another in a graph, or when they are written as a split function, we get our solution, which exactly matches this one. So yes, using the classical approach, we can solve equations where there are parts which are not continuous, or perhaps nice. But the fact is that Laplace transform does it, let's say, with more elegance. It's a better suited tool, and also computers can do this easily. It's much harder for computers to reason than for humans, we know that. And this requires quite a bit of reasoning. It can be programmed, no problem there, but it would be, let's say, difficult programming. It's much easier to teach computer just a few basic rules, essentially this, for the Laplace transform, and the computer can solve equations like that easily, and humans too. Once you teach computers or humans Laplace transform, you can use it to do all kinds of stuff. For instance, you can solve systems of differential equations. Now, this is a very simple system with constant coefficients, homogeneous. I could make it more interesting by adding right-hand sides, which are perhaps not continuous, things like that. But I just want to make a point. So let's apply Laplace transform to both equations. That's the whole point. So what will be the outcome? Well, on the left, we are applying Laplace transform to derivative of a function. There is a rule for that. We have to write s, and then we apply Laplace transform to y1 itself, and the outcome will be capital Y1, s. No problem there. And there is a tail. I have to subtract y1 at the origin, which happens to be 1. Why not? On the right, linearity, so 2 is out. Laplace transform applied to y1 is capital Y1, plus Laplace transform applied to y2 is just capital Y2. Easy. Let's play with the second equation. S y2s minus 1, that's the rule for the derivative, applied to y2, is equal to capital Y1 plus twice capital Y2. Okay, that's a system. It's a linear system. It's algebraic system. So perhaps I should move y1, y2 all to the left, and I keep forgetting to write the arguments. So perhaps I will drop them altogether. Okay, so I'm moving y1s to the left, y2s to the left, and I get the following system. y1 is taken how many times? S minus 2. S minus 2y1. Then there is y2. I move it to the left. It becomes minus y2. Then there is minus 1 left over, so I put it on the right. The equation is no longer homogeneous. Okay, that's life. Over here, y1 to the left, it becomes negative. Negative y1. y2 to the left, it becomes plus s minus 2 y2. And 1 to the right. So that's the system of algebraic equations which I'm supposed to solve. I could use intuitive elimination or Gaussian elimination. When you have a system with functions, sometimes it's actually interesting to use the Kramer rule, which you normally never use. So here's the Kramer rule. What is the determinant of the system? Well, I'm looking for the matrix, which means I'm looking for the coefficients. S minus 2, negative 1, S minus 2, and the determinant is S minus 2 squared minus 1. Do I want to play with it? That's a good question. Do I feel like playing with it? Well, perhaps I should. S squared minus 4s plus 4 minus 1 is plus 3, which is, when it comes to it, s minus 3 times s minus 1. So perhaps it was worth playing with it. I like that. Okay, let's find d for y1. Let's call it d1. So I'm looking for the determinant where the first column is replaced by the right-hand side. 1, 1, negative 1, s minus 2. So s minus 2 plus 1 is s minus 1. Okay. D2 is determinant. Now the first column is kept, and the second is replaced by the right-hand side. The same story. S minus 2 plus 1 is s minus 1. This is sort of boring, isn't it? Okay. Y1, Y2 is this determinant divided by this determinant, and I get 1 over s minus 3. And for y2, I get exactly the same. Did I say that this is a very simple system? Yeah, it's almost boring. Okay, I have y1, I have y2, and therefore I can pass to the inverse Laplace transform. I'm looking up 1 over s minus 3 in my dictionary. 1 over s minus 3, that's exponentials. y1t is e to 3t, y2t is e to 3t, t greater than or equal to 0, and we are done. So it seems that the Laplace transform is quite capable after all. It looks like a nice, useful transformation. Interestingly, one of my friends works in a certain applied area, and he told me that when they have a problem, they describe it, its components and how they are interconnected, to computer using the language of Laplace transform. Then the computer solves the problem, and they look at the answer, and they interpret this answer for the real world, again using their knowledge of Laplace transform. So they are not really using Laplace transform as a tool for solving problems, but as a tool for communication, which I found really interesting. Anyway, we are almost at the end. There is one more thing I want to show you. Let's have a look at it. In applications, you quite often encounter phenomena that are periodic. And if you want to apply Laplace transform to that, you have a little bit of a trouble. Let me show you. A periodic function, but now in the world of Laplace transform, we expect our functions to be 0 for negative t's. And if a function is periodic and 0 here, it must be 0 everywhere. So in the world of Laplace transform, there are very few, just one, periodic function, which is unpleasant. So what we do, we tweak the definition a little bit. In the world of Laplace transform, when we say periodic or periodic on 0 infinity, what we really mean that there is some shape on the interval 0t. It's a basic shape, very important for us. Let me emphasize it. And this basic shape is then repeated over and over. But only going to the right, not to the left. That's the whole point. So we have our periodic function. And a good question is, how do we transform it? And we definitely do not want to go by definition. This is typically a very bad idea. Fortunately for us, there is another grammatical rule, the last rule, Let's have a look at it. We have a function periodic on 0 infinity, that's the new notion, and we look up the basic shape and call it ft. So this part will be called f capital T as a subscript. And then if you want to transform the whole periodic function, it's enough to just transform this one basic shape and then do something to it using algebra. Okay? Let's prove it. We are trying to transform our periodic function, and I'm going to add the Heaviside function in it for a good measure. This is the last slide of the transformation part, and this is the last proof of the whole course. So it's a special proof. Let's enjoy it. By definition, integral from 0 to infinity ft ht e to negative st dt. So far, so good. We are integrating over the interval 0 infinity, and there's this basic interval 0t. I'm going to split this infinite interval into infinitely many intervals of length t. So it's easy to figure out how they look like, if they're all supposed to have length t. And I split integral over this whole thing into integrals over the individual intervals, so it will be infinitely many integrals which will be summing up. Summation sign, using k to cycle, and the integral from ft ht e to negative st dt will be taken between, here it comes, the basic one is 0t, that's the one that I like. And then, to get to the other intervals, I'm going to shift by t, or by 2t, or by 3t, and so on. So I'm shifting by kt. In this way, I just created infinitely many integrals, and I'm summing up k ranging from 0 to infinity. Is that right? When k is 0, I go from 0 to t. When k is 1, I go from t to 2t. Yeah? It fits. Those intervals are going one after another. When I put them together using summation, I get interval 0 infinity exactly as needed. Okay, here it comes. My next step is replacement. Instead of t, I'm going to use u plus kt. Or if you want, u is t minus kt. This is a linear shift, so du is definitely dt. No problem there. Let's see. My infinitely many integrals are now transformed into integrals from f u plus kt, Heaviside function u plus kt, e2 minus s u plus kt du. And the interesting thing is, what are the limits for my new integrals? Let's have a look at it. Well, lower limit, 0 plus kt. That's the limit for t. T is kt. When I subtract, for u the limit is 0. Wonderful. Let's have a look farther on. The top limit, t plus kt. When I substitute for t, kt cancels, and I get t. So now all these integrals are taken from 0 to t. I'm integrating between 0 and t all the time. Nice. Let's move on. I have infinitely many integrals, which is a bit unusual, but okay. So far it didn't cause troubles. What is this thing? U ranges between 0 and t, and I'm moving more to the right. So I'm integrating over these segments over here, but the function is t periodic, so it's the same as integrating over fu. Things are getting interesting. I'm integrating over the interval 0t, which is positive numbers, and if I add kt for any k, 0 or more, this is still positive, or 0 at worst. So this Heaviside function is 1. I can ignore it. I'm going to split the exponential as e to minus su times e to minus s kt. That's an important moment, du. Here we go. Summation, k ranges from 0 to infinity. I pull out this exponential, and I'm going to write it in a slightly different way. E to negative st to power k. And what is left? Well, integral between 0 and t, fu e to minus su du. And this is where it gets interesting. All these integrals are now the same. They don't depend on k. And therefore, I can pull them out of the summation. And this is nothing else but the Laplace transform of the basic period. Because we are integrating from 0 to t. This function f is restricted just to this range and considered to be 0 elsewhere. So this is really just a transformation of ft. And it's multiplied by this summation. And for this summation, I can use the formula for the sum of a geometric sequence or a geometric series, whichever way you look at it. So for that, we know that the formula is 1 over 1 minus this number in the bracket. And unless I'm mistaken, this should be the formula from the theorem. And it is. Wow, we've just done it. So that was the last proof of the course. And it wasn't bad, I think. It was nice, and we got some review of substitution, things like that. Beautiful. Anyway, that was the formula. So for the last thing, to finish it off on a high, we want to find Laplace transform of sine t, which is absolutely easy, so I'm going to spoil it by adding absolute value. Let's see. Dictionary. No sign in absolute value in our dictionary. Let's have a look at the grammar. No rule for absolute value. Okay, what can we do? We don't want to go by definition, remember. Well, let's have a look at it. We are trying to transform a function that looks like this. It's 0 up to the origin, and then its sign in absolute value. So this is the function that we are trying to transform. Is it periodic? Yes. The period is pi. So we can apply the formula which we just proved. Okay, I switched the slide, so let's have a look at it here. 1 over 1 minus e to negative pi s, because pi is the period. And now we have to apply Laplace transform just to one basic shape, which is this little hill given by sine function between 0 and pi. And this is a finite signal, so we can actually do it using the description which features the sine function, which is in our dictionary. And the heaviside functions, and for that we have those rules over here, which we developed today. But by a remarkable coincidence, exactly this Laplace transform we did, I don't know, half an hour ago, some time ago. And if my short-term memory is correct, then the outcome was 1 plus e to negative pi s and the Laplace transform of the sine function. I think that was it. Let me rewrite it again. It's strangely symmetric when you write it like that. Interesting. Intriguing, I would even say. But anyway, that's the result. Nice. So that was the last example of this lecture and of the part called transformations. And this is it, not just for transformations, but also for ordinary differential equations. So I hope you enjoyed it, and see you next time. We have one little lecture still to cover, and then we are done. See you there.